A force is any push or pull on an object. The units for force are newtons, and they are equal to kilograms times meters per second squared. Force is equal to the mass times the acceleration. Weight we write as F sub g, or sometimes a W, okay? And that's also equal to mass times gravity, gravity being 9.81 meters per second squared. It says mass is the amount of matter in an object. Mass doesn't change, okay? Your weight changes, but not your mass, okay? The mass is how much matter is actually in the object, okay? So weight gets less as you move away from the center of the earth. Closer to the center of the earth, you weigh more because gravity pulls stronger closer you are, all right? All right, Isaac Newton had 3 laws. The first law is the law of inertia. An object at rest will stay at rest, an object in motion will stay in motion unless acted upon by an outside force. I included this video here you could watch. This is an example of Newton's first law on the International Space Station. Okay. Basically, inertia means mass. Okay. If something has 100 kilograms of mass and something has 200 kilograms of mass, the thing with 200 kilograms has twice the amount of inertia. And inertia means resistance to change. Okay. So if the object's moving, it'll stay moving. If the object's not moving, it doesn't want to move. Okay. Think about it if you like this. If you've ever tried to push a car that was not moving, all right, maybe the person pushes it in puts it in neutral, and then you get behind it and you start pushing, all right, it takes a lot of force to get that thing to move, okay? But once it's moving, it requires less force, okay, because now the object's already in motion, it wants to stay in motion, okay? The second law is F equals ma. It says an object will accelerate in the presence of an unbalanced force. Unbalanced force would be like if you're pushing this way with 10 newtons and the force of friction opposing it is 5 newtons, that would be an unbalanced. But if force of friction was 10 newtons, then that would be a balanced force, and it would not be an acceleration. Okay? So the larger the mass, the smaller the acceleration. Now, I like to use this analogy here. F equals ma, or F equals ma. When you look at that, if you have a small mass, you have a large acceleration. If you have a large mass, you have a small acceleration. All right? They're inverse, okay? Another video, International Space Station on F equals ma. You can watch that on your own. And then the third law is for every action, there's an equal and opposite reaction, okay? Let's say you have a tennis racket and a tennis ball. You swing to hit the tennis ball, okay? The amount of force that you hit that tennis ball with, that tennis ball pushes back on the racket with an equal and opposite force. What happens? Well, the force of the racket causes the ball to accelerate, but the force the ball is on the racket causes the racket to decelerate, okay? And the bigger the mass, the less change in the acceleration, okay? If you're driving down the road and a big old butterfly is flying across the road and all of a sudden your car hits it, all right, hits the windshield, theoretically, your car will slow down a really, really, really small amount because that butterfly is very, very small mass, okay? Now, the force that you present on the butterfly is the same as the butterfly presents on the car. So the force that you present on that little tiny mass would accelerate extremely quickly and it'll just splat, okay? All right, so that's Isaac's third law. Now, apparent weight, okay? And like I said, sometimes we use W, sometimes we use F sub G. Apparent weight is your weight with respect to the direction you're accelerating, okay? Take an elevator. If you get in an elevator and you hit the button for up, as soon as it starts moving up, you feel heavier, okay? If you were standing on a scale in an elevator, you would actually increase, all right, for maybe half a second or two, all right, because as long as the elevator is accelerating upward, you're adding gravity to the acceleration. Times your mass, you weigh more, and that's an apparent weight. Now, if you're at the top of the floor and you hit down when it first starts going, you feel almost lightheaded, and that's because gravity's pulling down, um, and the acceleration of the elevator is down, but because you're standing on the floor, the force back up, all right, causes basically like a deceleration, all right? So whenever you feel heavier, it's because you're accelerating upward and the floor you're standing on is accelerating underneath your feet. That's why you feel it. If you're accelerating downward, then you're literally almost like falling on top of the floor. So that reactive force is not as strong. Okay, so if we use this in terms of tension, also, like if you have a bucket of water and you're in a well, when you're winding up the well water to get the bucket up, all right, that's going to feel heavier than if you were lowering the bucket down in. Okay, so anytime you accelerate up, you feel heavier. Anytime you accelerate down, you feel lighter. If you're traveling up or down at constant speed, there's no acceleration difference, and your weight will be your normal weight just standing around. Okay? And those are the things you need to know about that. Okay, so yes, if you're moving up or down with constant velocity, there's no acceleration. Therefore, your apparent weight is the same. It's just mg. All right. So an elevator, think of all the times when riding in an elevator you feel heavier. It's when you start going up or you stop going down. When do you feel lighter? When you start going down or when you're stopping going up. All right. Because you're stopping going up, you actually accelerate, you're decelerating, you're accelerating downward. Okay. So anytime you're accelerating downward, you're going to feel lighter. Anytime you accelerate upward, feel heavier. And this is just an example math of person. If you notice, he's standing on a scale. All right, so he can feel that force between the floor and his feet. All right, so in this case, he is accelerating upward at 2.5 meters per second squared. That's gravity. His mass is 70. He would weigh, apparent weight, 861.7 newtons.